finish up talking about the scalar field. So what I really want to do is kind of finish saying what there is to say about a free relativistic scalar field, and especially about how kind of symmetries act upon it. So at the end of the day, what we really want is we want to understand how the Lorenz group acts. So how translations act, how translations in time, the Hamiltonian acts, how the spatial rotations act, and how boosts act, and so construct those operators on the state space of the theory and on the operators of the theory, and show that they have all the right commutation relations that we've produced. This theory we've produced, its state space is, as expected, a unitary representation of the Poincare group. And then I'm going to move on to not thinking about space-time symmetries, but to thinking about internal symmetries. That if you've got multiple degrees of freedom, and you can have some group acting on the degrees of freedom at a point, not moving you in space and time, but just, and these are going to correspond to phenomena like charge and various generalizations of that. So that's what we're gonna do today. Okay. Okay. So I thought just to finish up one topic from last time, which was about propagators. And so remember, I mean, one thing I did was so this was something that in non-relativistic QFT you could calculate. This was the standard kind of the standard propagator for a free particle. We've talked about various times, but you could think of it as being, if you wanted to compute it, one way to compute it would be to take the vacuum state, act on it by the field, act on it by the field at let's say at time 0 at position 0, and then annihilate it at either field operators at some t, an x vector, and then so you calculate this thing, and you find something like, let's see, did I write this down? Well, I think I wrote this down last time. Maybe I won't write it down, but you just get just the standard thing that we've always seen for the for how the free particle moves in how the free particle wave function evolves, using, it's kind of the kernel for the evolution of the free particle wave function, and it anyway. So there's this, but now for the Klein-Gordon equation, so relativistically, the relativistic case, we don't actually have the scalar field that we're talking about doesn't actually have have kind of separate it's its own adjoint. So instead what you have is just this. The analog is just you at time 0 you do something, and then you act on it at some position, and then hit it with this guy again, 0 x vector. So you compute that, but the confusing thing about working with a real scalar field is that it's got both. It's self-adjoint. It doesn't have a adjoint. It has kind of built into it adjoint and creation and annihilation things for quanta, which are corresponding to, if you Fourier decompose the thing into the positive and negative energy pieces of it. And so I think if I actually did this calculation, what you get is 1 over cubed, the integral 3 e to the omega p. Okay, so it's and another way to show this is not obviously relativistically invariant, but you could also this had another expression 1 over 2 pi cubed integral over Minkowski space, where you look just at the positive energy light cone, and you stick to the light cone, and then e to the x. So this is the kind of these are the same by this manipulation of this delta function which we talked about, and but this is the anyway, and so this is this is obviously easy to see this relativistically invariant. Here it's less obvious, but the thing to say about this is actually a very kind of it's kind of a tricky thing. I mean, what you're doing is you're integrating over over the positive mass shell. Sorry, this is the positive mass shell. You're integrating over the positive mass shell this kind of phase, and your integral is going off to infinity. So this is not at all a convergent integral, and so I should say that this is a distribution. Okay, this is not a definitely not a function. So you have to integrate this thing against the right class of well-behaved functions of p. Functions of x. So you have to integrate these guys against well-defined some well-defined function of some well-behaved function of x, and you can then get to get something that makes sense. But I think I probably should. I was thinking of saying a lot more about the kind of trickinesses of this guy. Let me see what I'm maybe. Not sure how much. I mean, you can get into the trickinesses of this distribution in several different ways. Maybe let me just give you some properties of this. And okay, so one. Let me just, there's something, actually there's another, so you can also write this, I think I did this also last time. You can write this somewhat more explicitly. This integral has a, has a name that it's m over 2 pi squared and then this okay, and so what's actually the behavior? There's several things to say about the behavior of this guy. So the behavior, maybe one thing to say is that as a function of so let's look in time and x. So the standard thing about thinking about relativity is that you're going to have these regions here, which are so here and here that are time-like, and you're going to have these regions here, here and here, which are space-like. And so the what happens with this guy, if you look at the behavior of this thing, it depends a lot on this on what this thing is doing, and on the sign of this, which is the sign of whether you're zero, you're on the null cone, or you're time-like, or you're space-like. And what happens here, space-like, it's going as e to the minus mx. So this thing has this behavior of being, if you look more closely at the behavior, at what the definition of this function and what its asymptotic properties are, you could show that it goes as it falls off exponentially in space-like direction. So as you go this way, and time-like, it's but this actually here, this actually is a real function. So behavior in space-like is kind of as a function. It's not only a distribution, but here you've got a time-like. You've got various terms going like e to the I mt, and it's really a distribution. And then maybe another way to think about it is to take z is equal to t plus I tau. Is to do this calculation for time complex, and then what you find is then then here you have x vector, and here you have minus x vector, and here. And the distributional the problem with it only being distribution corresponds to behavior in the time-like. This is time-like. Oh, this is time-like. And so there's actually, if you know about complex functions, there's a branch cut, and you have to in order to say what this thing is doing, you have to kind of define it as by taking the limit as you approach the branch cut from these two possible directions. So there's kind of two possible ways of making sense of what this guy really means in the time-like case. Either whether you're coming in this way or you're coming in this way. If you're in the space-like area, space-like, then the thing is perfectly well defined. It's a perfectly well defined function. You don't have to think of it as in any kind of limiting process or something. And the other there's another whole kind of approach to making sense of these quantum field theory calculations, which I haven't really emphasized in this class, but which I think is actually really important. Is that what you should do is you should always think of time as being a complex variable. And you should always define your theory along here. So along here, this is often called the Euclidean region. So in other words, here you have so if you take the complex part to the real part to be zero, and just look at a purely imaginary part, then your notion of distance is going to be the normal one. Instead of minus t squared plus the distance squared, it'll be tau squared plus the distance squared. So it'll look like the whole problem will have kind of a nice four-dimensional Euclidean symmetry, and so one whole approach to this whole thing is to actually define. And this is what you get into, especially like if you want to do numerical calculations, for instance, and you wanted to find a path integral or some other form of the theory, you actually want to define it along here, and then define it for real time for t by analytic continuation from here, and you use the fact that if you have a holomorphic function of a complex variable, and if you know it along this axis, you can analytically continue and and figure out what it's going to do on this axis, and then you just have to watch out that it's going to do different things depending upon whether you approach it, which you have to approach it by some kind of limiting process, and depending which direction you come at it, you'll get different answers. Okay, so that's kind of the story about the propagator.
Explicitly, what's like this K1 function?
It's a modified Bessel function. You can define there's various integral formulas. You can, one way to get it is to kind of you can turn this into a one-dimensional integral by playing around with it and choosing coordinates, and then that one-dimensional integral is one definition of what K1 is, or you can or you can define K1 as it's the thing which satisfies a certain differential equation, but it's not an elementary function. It can't be written in terms of sines, cosines, exponential, but it's a modified Bessel function. But the slightly funny thing is here that you're so when you're time-like, your problem is that it's got an imaginary argument. So you have to understand this modified Bessel function and its behavior as as the argument goes complex. That's the trickiness to this. Okay, so that's one. Think about it. And then the other thing to think about, and so as I think I pointed out last time, so there's something a little bit funny about this, that this seems to be saying that if you're if you're creating a particle, it's going to have some amplitude. If you try to give this the same interpretation as for the non-relativistic theory, you would say, well, you're creating something. That this was creating something at a certain time. Well, it's going to have some non-zero amplitude outside the light cone, which you would think might violate causality. So let me just say something about what that is. And the point is that this phi operator, this real phi operator, is doing something a little bit tricky. It's not just creating a particle. It's kind of, in some sense, it's creating a particle and annihilating a particle at the same time. And you have to, so if you want to kind of make any physical sense of that, you have to think about that. So the thing which kind of tells you that causality is really going to be all right is this next calculation. Okay, so what you do is you can calculate the commutator. So and then what you get, if you do this calculation, it's same kind of calculation as you had before, except you're going to you're going to use the commutation relations for the A and A daggers, and what you end up with is you end up with this. You end up with 1 over 2 pi cubed, then an integral q vector, and then you have the same kind of contribution, the same thing you had before. But then you have a contribution from the opposite ordering, and that looks like this. Okay. So you have something like this. So now it's kind of the difference of these two distributions of this kind. And what you have, and this has these properties. Well, one, that I want to say, this still has the same, so non-zero. So again, it's still non-zero distribution for tx, tx time-like, but it's actually equal to 0 for tx space-like. So the story is that if you've got a, so this is 0 in this entire region. So the commutator is doing something interesting, and there's some interesting, and you know, these are behaving like interesting operators in a quantum theory, like the Q of t's and the P of t's at different times in a single particle theory, but it's 0 everywhere. It's 0 everywhere that's space-like, and it's 0 kind of for an interesting reason, because you've got something. This is behaving like e to the minus mx, and then this is behaving at anyway. Yeah, so this is so you've got two terms that are both kind of looking like e to the minus mx at large distances. They're non-zero, but then there's a minus sign, and you can show that and these things cancel exactly. So one way to show this is that so at t is equal to 0, they're the same. So if you set t is equal to 0 here, then you're just integrating e to the I p dot x over e to the I p dot x here, and e to the minus I p dot x here. But this integral, if you just take p to minus p, this integral and this integral are going to be they're the same integral, and you just can't, and you can just can't, and so the amplitudes cancel. Same integral. You can take, p vector, just change variables. P vector goes to minus p vector, and so this tells you that as t is equal to, so the thing is 0 along here, and then use Lorenz invariance for the rest of the. And so what Lorenz transformations do is they take this t is equal to 0 thing here, and then and then they kind of move it to some t or to t prime, and so if you know that you've got something that's 0 here and it's Lorenz invariant, it has to be 0 throughout the whole space-like region. And so you can interpret. I mean, this tells you various things. One thing is it tells you, well, you can, so what's happening at each, the operators that are kind of giving you your initial data at each corresponding initial data at each t are all simultaneously diagonalizable, which is what you expect. All of these at t is equal to 0. All of these operators they're all your canonical variables, and they correspond to all your possible q's, and so they're all commuting. They all have 0 plus home brackets with each other. You've basically got a it's a phase space with this phi of x for different x are basically your q variables, and they all have 0 plus home brackets with with each other, and can all be simultaneously diagonalized. And so this is what you expect. There's this, and if you want to kind of give a physical interpretation to this business of what, if you want to try to interpret these things, these terms as corresponding to, well, anyway, so this is, you can see that this in some sense is what's going to restore causality. It's also, and it's restoring. So what would have wrecked causality would have been having this having these guys not commuting at space-like separations, because then you could use this to send a signal from one point to another space-like point and to measure it and get back and you could actually affect something that was happening at a space-like separation from you. Okay, so that's the and you can see and it's kind of absolutely necessary that this be so it's necessary that these things commute not just at t is equal to 0, but at all space-like separations, because one thing about if you have two different points that are here and here that are space-like separated, there isn't actually a well-defined notion of which one is later than the other, because if I've got here. Anyway, so for this notion of time and this notion of time, this guy is after this guy. But if I, if I change, well, I don't know, maybe I haven't drawn this right. But if I move this even farther this way, then this guy will become before this guy. So there's no Lorenz invariant when two points are space-like. There's no way of saying in a Lorenz invariant way which happened before the other. So if you want if you want to be able to make sense of the world with causality, then you better not be able to. You have to have a condition. You have to have this kind of condition. And so this is a condition here that you can actually check and you can calculate for the free field theory. It's actually even if you have an interacting field theory. So there's a set of axioms that you can kind of create and try and study. Interacting theories where you've got some kind of Hamiltonian that's got terms in it which are not just quadratic, but higher order terms which are going to cause these particles to interact with each other and to do interesting things. And even so, and but just for these basic reasons of causality, it's kind of a basic assumption about even interacting quantum field theories that they obey this. They obey this property that they're space-like commutators that are B0, and it's not just for free theories but also for interacting theories. And so the basic axioms for interacting theories are this kind of causality axiom, and then a Lorenz invariance axiom also, that if you start computing things like the propagator and higher order versions of it, that you're going to get your answer is always going to be Lorenz invariant. So those are kind of the two basic kind of axioms you use to try to axiomatically talk about interacting field theories, but they're certainly satisfied by this case. Okay, I think, let me see if there's anything else. Yeah, I guess that's it. Yeah. So I'll stop talking. So that's all I want to say about the propagators. There's various other things. Anyway, there's a long story about how you manipulate these propagator functions and get sensible results. But I won't go into that. This is kind of all we need for what I want to tell you about here. So any other questions about propagators before I move on? Okay, so let's go on to the next. That's in some sense the end of what I wanted to say was in chapter 43 here. But now if we want to get on to the symmetries. So, Okay, so maybe it's a good idea to just to say what I'm trying to do. So what I'm trying to do is, we know, so the problem is to find, so show that the we know that the the Poincare group should act unitarily on the QFT state space. Okay. And what I want to do is want to find the Lie algebra. So anyway, so H is a unitary of Quadratic. And so the problem is to find the Lie algebra representation operators. Okay. So this is so this multi-particle theory, we've created it as by looking at the state space, which is a kind of by taking symmetric tensor products of the single particle state space, and we've got various operators acting on it. But we know that the Poincare group acts on the single particle state space. It's just because that's just the positive energy solutions of the Klein-Gordon equation, and the Poincare group takes one, commutes with the Klein-Gordon operator and takes a positive energy solution, a positive energy solution. So we should also get a representation on the full Fock space and we want to know what it is in the Lie algebra. And so this is the same. So the idea. So this is an infinite dimensional version of the finite dimensional case. And then so I spent a lot of time playing around with operators. So there you had M. You started out with some phase space M, and you're going to quantize it, and and get this representation, which was which came from the representation of Heisenberg Lie algebra. So, but this was finite dimensional. Let's see, what did I want to say about? And in the finite dimensional case, what you had is so this came together with this came together with a Poisson bracket. You had a group SP of 2D R, which was the symplectic transformations that acted on here, and then you had a projective. Well, it's a representation up to this funny projective factor of this guy on the state space, which you got from the Heisenberg representation, and that this was the Lie. So acts up to there's a problem in the phase factor, and then you had quadratic, and the Lie algebra action was quadratic. You had in P J QJ. So you had various. So the Lie algebra of this guy was was given by quadratic things in these p and q variables, and then what you did give are the Lie algebra. And so you quantize. So you just quantize qj goes to qj, qj, big pj. And then you just have to be a little bit careful about the ordering. There's an ordering ambiguity problem at a certain point, and that causes the need for this. Anyway, that causes this to just be a projective representation, and you deal with that. Okay, and so but the next part of the story was that if you pick, given a complex structure J, then what you can do is that these guys then become Z, J, and Z bar J. So you can then break up this space, this complexification of the space with these guys as a basis to one with these guys as a basis, and then you quantize. And Zj goes to a creation operator, and Z bar J goes to an annihilation operator, an adjoint. And this is so this is what I call Bargmann-Fock, and what I call Bargmann-Fock. Okay. And then the next part of the story was that. So U is that you have a J gives you a U of D subgroup of SP of. So this was the symplectic transformations that commute with this choice of complex structure with this operator J, whose square is -1, and so. These guys, and then what we showed was that the let's see this, yeah. So then, so now, if you look at if you look at symmetries, if you look at group actions which act on your original phase space and preserving the Poisson bracket, but that they also preserve this guy. Then they live in this unitary group, okay? And so what's going to happen for all of the symmetries that we're interested in that are going to act on this act on the Klein-Gordon theory? They're going to commute with, in this case, J was the thing which was plus I on positive energy things, negative I on plus I on positive energy things, negative I on negative energy things, and so we're interested always in these in group actions which can preserve this distinction between positive and negative energy, and so we're interested in in finding not so our Poincare group is a subgroup of basically of, you can think of it as U infinity, because so we're taking D is going off to infinity, because now we have a degree of freedom for each possible momentum, which is SP. Okay, so we're interested in some very, very special. There's some infinite dimensional group of all kind of symplectic transformations of this space of solutions of the Klein-Gordon equation that preserves the distinction between positive and negative energy, and that's this group. We're interested in some very special ones, which come from the Poincare symmetry of the whole situation, and so this is a finite dimensional group. So we want to find find the quadratic operators that give the Lie Poincaré representation on the full Fock space. And so the finite dimensional analog of what we're trying to do is, if you go back and look at all these finite dimensional calculations that were so for finite D, what I remember what I did was I took a element of the Lie algebra of U of D. So it's just a D by D skew adjoint matrix. And then what I did is I defined U A prime. So I defined the quadratic operator that we want. It was the sum over JK. A dagger J A J K A K. There's this guy. And we showed that this had the properties that it does this. U B U of AB. Okay. So in other words, so these operators give you a Lie algebra representation. Sorry. Give you a Lie algebra. So this actually has the right. This is a Lie algebra homomorphism property. So these are going to be quadratic operators that act on this on this Fock space. And they also had this property. You could also calculate what they did. Let's see. Well, you also had something like this. You also had U A prime A dagger. And now think of this guy as being, in order to avoid writing indices, I'm going to write this as being just the transpose of dagger, right? And then U A prime A, right, minus A. So think of this these formulas as these are matrices, and think of these things as column. As I've just put all of the annihilation equation operators into column vectors like this. And they've done this. So the kind of in finite dimensions, I kind of went through all of this, and so we're interested in really now, instead of A being a matrix, it's now in some sense an infinite dimensional matrix with dimensions parameterized by the various possible values of P. And then the question is, what is it? So the examples that we, okay, so there's some obvious, well, anyway, it's the easy to see cases is that for translations in X and T, then Lie. Then A is diagonal. No, in this index P vector. In other words, if you think of these indices now as depending on the continuous indices P and P prime, it's going to be, so A is proportional to, well, to delta of P minus P vector prime. And what you get is for the so for translations in space, this A operator is just is just the up to a factor of I is just the momentum itself. So you get, I think I kind of said this last time. So you get P vector, that the operator is going to be the integral over arc. So your your sum over two indices becomes a sum over one index because it's a delta function, and you're just integrating over the possible p's, and you're getting the diagonal entries are the things which on the single particle space generate translations, which are the momenta, and then a dagger vector, a p vector. Okay, so there's that, and then you get the same thing in time. Let me guess. And again, sorry, in both of these cases, I guess I have there's a d cubed p vector. Okay. So these are the so these are kind of the translation part of the translation part of the Poincare group action. Now for the other parts, let's see, you can do. I got these. Yeah. So for rotations. So for spatial rotations, the Lie algebra elements expressed in terms of x and p are going to be given by this L vector is equal to x vector plus p vector. Or if you like, you're going to, and then so as operators, you're going to have an L vector is big x vector plus p vector. So this is the angular momentum operator on the single particle space. Just when I was working with single particles, I called this q, but now I'm calling it x. But it's the same. It's just the q cross product with p. And then, but if we want to write this, see what this is going to do to these things that are indexed in momentum space. What you want to do is you want to Fourier transform this so that not that x is diagonal and p is a differentiation operator, but if you think of it in Fourier space, it's going to be I guess yeah. So here in x space, this is minus I rad x, but in the Fourier transform version of this is going to be minus I p vector. That's our p. That's your p vector. So it's just the Fourier transform of this, and I hope I got the signs right in this. I'm not convinced, but anyway, the yeah. Okay, and so what you want to do then is you want to think so this is what your rotations are doing on infinitesimally on H1 on the single particle space, and so this is your analog of your A, your Lie algebra element that you want to create a quadratic operator out of. Except it's no longer quite diagonal in P because this differentiation operator is not diagonal in P. This is diagonal in P. This is not really diagonal in P. But what you want to do is that this implies that you can take the angular momentum operator, the thing that when you exponentiate it will tell you what rotations are going to do on the Fock space, is just going to be just this guy. It's just going to be the integral over r cubed now you just take a dagger of P. Yeah, a dagger of P minus I. So it's just going to be this guy. And then similarly for boosts, for boosts, what you had was that you had this k vector, which is so you can think of the various components of the angular momentum as just infinitesimal generators of rotations in two spatial planes. Well, the boosts are kind of infinitesimal generator of rotations in a plane in 4 dimension, which is one direction is t and and the other direction is spatial. So you end up with with the analog of this formula, which is something like anyway. You have to kind of also keep straight how to get self-adjoint operators, but it's going to be well. Let me just write down. So anyway, you end up with an I omega p, yeah, k vector u vector that grad u vector. So instead of you're always so the fact that you're going in the time direction. So as you went to the different spatial directions, you had the different spatial components of P. Here you're going in the time directions, so you just have the energy, which is really the time component of the energy momentum. And so then you had k vector is r cubed, and then if I've got this right, it's an I omega p vector. A vector P grad P A of T. Okay, so now so what you can show is that minus I. Okay, so these have all been written so that these are all self-adjoint operators. You can check that they're all set to be self-adjoint. But if you want them to be the skew adjoint operators that generate the Lie algebra action of the Poincare group, you just put in a minus I, and so that minus I p vector minus I h minus I L vector minus I k vector, and so all of these operators, satisfy the Lie Poincare commutation relation. And all of you should be able to show any of the commutation relations between two Lie algebra elements of the Poincare group, should correspond to the commutation relations of these guys, and you just use, just need a p vector. So if you want to actually do you can check that I've got the right commutation relations by just working out what the commutator of any of these two things is, and you should be able to do it just using these relations for the operator. So it's all and this is all it's a fairly straightforward generalization of what we did in finite dimensions, except figs are now continuously indexed. Okay, so that's now the okay, so I spent a lot of time. Okay, now the problem with all this is all of this is really nice in momentum space, but you really actually, for various reasons at various points, and for better or worse, also the way I explained it in for the next thing I want to do, which is for the U1 symmetry, you want to actually be able to work not with, you want to be able to work in position space, not momentum space. So in position space, okay, you have so you, instead of having, you know, analogs of quantizing Z and Z bar, you have analogs of your Q and your P's. And so one thing you can do if you want is you can write the you can use well, I think this I won't take the time to go through this, but you can use formulas vector in terms of A dagger P A. So there are these formulas we played with at various times, which are how you express the field in terms of these annihilation and creation operators, and you can just, yeah, it's fairly easy to kind of to play with those equations and find a formula for these guys to get a dagger P vector in terms of these guys. I mean, those formulas are just basically a Fourier transforms with it's the same relation that you have, like, you know, Z, what is it, Z is 1 over the square root of 2 of Q plus, I forgot whether it's plus or minus, but I P, and then the thing is that here you've really got kind of different your thing depends upon a you know, you have this kind of omega, which depends upon P, which is changing, but you can basically go back and just look at the standard formulas for the harmonic oscillator, and then you'll get you have Q operators and P operators, or you have Z and Z bar operators, and you have A and A dagger operators corresponding to Z and Z bar, and you can just use these formulas to go back and forth. So this is just there's another version of this. And then, so everything I wrote down, and you can then write from the algebra, write the correctly, rep in terms of these guys. And maybe just let me just write down. So write down. So you could do this by taking the formulas I derived, I kind of motivated and derived earlier, and then just do, you know, just rewrite it, just do the translation between just wherever. Anyway, find the formulas and plug in the formulas for these guys in terms of these guys, and you get a formula in terms of these guys. But it comes out to be something like, what is it? So P vector. Is it P vector? And it turns out to be something like, I've got the sign right, a minus R cubed, and then at of X rad. And the one thing you have to watch out with, if you're working with these variables instead of the A and A daggers, is you have to normal order. You have to the formulas that I wrote down before, they were written always assuming that I was looking for a normal ordered operator, and that was designed to kind of, anyway, that was designed to deal with the possible operator ordering problems that you get in these quadratic things properly. Well, here, so the formulas I wrote down have all been normal ordered, but automatically, just because the A daggers were on the left, the A's were on the right. But for these guys, you have to do that differently, and then you get the same thing. You get L vector is what. Again, is minus the integral of r cubed, normal ordered I hat of x vector, and then there's an x so you can write down the formulas in terms of in X space for these things. And what I think I spend some time in the book, I think, actually trying to motivate some of these things, so you can actually go back and work with the Klein-Gordon theory, as a classical theory, and ask the question, what is its phase space? And its phase space is going to have basis vectors pi. Its dual phase space will have basis vectors pi of x vector, phi of x vector, and what are the anyway, what's the Poisson bracket? What are the Poisson bracket relations between all these things? And you could go through that whole thing, and then you could actually derive these formulas, from first principles there, by knowing again, by knowing what these translations and rotations do on the on the solutions to the Klein-Gordon equation. You can you could do it there, but probably in some sense, the easiest calculation is is always to work in momentum space, where the momentum is a diagonal operator, and then here it's a little bit, anyway. It's always trickier. Instead of just having A and A daggers, you've got phi and pi's, and the formulas are trickier. Okay, so let's see. There's maybe the one last thing to say about that was I want to do this. Yeah. So and then one last one, I guess, is just translations in time, and those give you this more. The Hamiltonian is this more interesting thing. That the Hamiltonian is the function on the phase space which generates translations in time. And the problem with this whole formalism is that it's not it doesn't look relativistically invariant. So it's not the momentum is doing something simply here, but in terms of the time translations are going to be that give you the dynamics are not so simple in this kind of non-covariant splitting, and what you end up with is something like h hat is a half your integral over r cubed, and then you've got these guys pi hat of x squared. So there's just there's a pi hat squared, and then there's a phi hat, and then the Laplacian phi hat, and then there's a minus. Sorry, I think is there a minus sign? I guess here. Plus m squared. Okay. And so this more complicated looking thing, if you rewrite phi's and pi's in terms of A and A daggers, you get that much simpler thing, which I showed you before. So, which is kind of an argument for working in P space, not in X space. Okay, and then again, same story. You can you can calculate the commutation relations of any of these quadratic things just using the standard fact that phi of x commutator with pi of x prime is delta of x minus x prime. Using that standard commutator, you can you can show that these things satisfy the commutator relations of the Poincare group. Okay, so maybe I'll so that's the story about space-time symmetries. But it really is just showing that the theory has a unitary action of the Poincare group on it, and it's exactly the sort of thing that we it all comes, the action on the whole theory just comes from the action on the single particle space. And it's really just kind of an infinitesimal version of, we had a group acting on a vector space, and then if we then thought of the degrees of freedom of that vector space as degrees of freedom of a harmonic oscillator, then we get a corresponding action on the whole Fock space, on the whole state space of the harmonic oscillator. This is just kind of an infinitesimal version of that. Okay, so let's go on to the next thing. And this, let me start on this. Maybe I'll say a little bit more next time, but this leads into the next part of the class. So let me tell you about internal symmetries. So these are going to be groups. We're going to have some kind of nice Lie group, some compact Lie group, which is going to act on the theory. And what it's going to do is just maybe, and it's going to leave the space-time points alone, but it's going to. So these are what you have. Is you have, if you have multiple given. N, let me call it, I guess I call it M scalar field. So what you can do, so these are going to be, maybe I'll write them down classically, but they're going to be just, so now they're going to have some index vector to M. What you can do is you can look at, if the if you have the usual Poisson brackets, which are dealt with delta ij in the indices. So if you basically put together, just m copies of your scalar field, put together m copies of your scalar field, and the Poisson brackets are just the standard thing. So so the Poisson brackets between different j's are zero. You only get the usual Poisson brackets. This thing. Then you have an extra symmetry. Then you have a SOM symmetry of your phase space. So if you think it, and just basically by rotating, just rotations. So SOM of, now think of these as vector valued fields. Okay. So you've got your kind of canonical coordinates on your phase space are now these vector valued things, and you just act on you do what you do whenever if you had whenever you had kind of m degrees of freedom in a 2m dimensional phase space, the Poisson bracket had an SOM symmetry where you simultaneously rotate these guys and these guys in the same way. And so the simplest case that we're interested in is going to be m is equal to 2. So what I'm going to do, so what I'm trying to get at now is I'm trying to get at the case of what's normally thought of as a complex, instead of having a real scalar field, of having a complex scalar field. Now the problem with a complex scalar field is that I'm already doing something very funny with complex numbers and with the complex structure in order to quantize the theory. If these were actually complex gadgets already, then I'd have to kind of complexify a complex space in order to do my quantization, to do my Bargmann-Fock quantization, and that gets very confusing. So instead of what I'm going to do here is start by motivating this this complex scalar field by saying that let's just think of it as a pair of real scalar fields, and so and let's just have so it has an SO2 symmetry, but that's really that's really equal to a U1 symmetry, and we really could put these phi1 and phi2 together into a complex variable and work with it that way. But I want to avoid doing that for now. And so then what you do is so you have, actually maybe I put these down here. So you have phi1, phi2, phi1, phi2. And let's actually, maybe to just save some time, let me just get to the bottom line of where I want to get with this, is that I really, so you can think of these as complex things depending upon x vector. But or you can think of the corresponding operators, and they've just got the commutation relations are just the usual things, that this guy has non-trivial commutation relations with this guy and this guy with this guy, but everybody else is 0. But if you figure out what the SO2 is, the so you get an analog of 2D rotations where you had in 2D you had that this you had that UL, you had that the moment map for a two-dimensional rotation was like Q1 P2 minus P1 Q2. Right? So this was just a rotation in the 1-2 plane. That this was the quadratic thing in P's and Q's that gave you that generated that was this thing. And then what this is finally going to, what you finally do with all this is this. You end up with so this is just kind of going to be the same story, except P's and Q's separately have x vector dependence, but what I'm talking about commutes with the x vector dependence. So what you end up with is this. Let's see, the Q vector. So you get a Q. So so you get an operator I've got to call Q. That's going to be the self-adjoint one. And so the thing which is skew adjoint, which is the so this is going to come from a Lie algebra rep of SO2. 2, and so the Lie algebra of SO2 just has one direction. It has one. It's one-dimensional. So you just need to know what this is. So this is in some sense this kind of pi prime of since the basis here is something I call L maybe. Well, the pi prime of L is just this guy, and it's skew adjoint. And what you end up with is you end up with this guy as minus I interval of pi 2. So you're basically using, well, it's yeah. So it's basically just this guy. So you have a pi 2 and a phi 1 and a pi 1 and a phi 2, and you're going to get so pi 2 the x vector pi 1 and minus pi 1. So anyways, this is an operator, and it anyway you can figure out what its commutation relations are if you commute this guy with a phi 1. You're going to get plus or minus a phi 2. It's going to interchange phi 1 and phi 2. It's going to rotate you in the 1-2 plane. Okay, this is really a rotation in the infinitesimal rotation in the 1-2 plane for how these guys are labeled. And then and if you go back into or you can then go into momentum space, and getting rid of the I, you can have Q hat is I interval dQp, and then here you have an A2 dagger, A1 of P vector, A1 of P vector minus A1 dagger, A2 of P vector. Okay. So that's what this is going to look like in momentum space. Again, it's just a quadratic thing, and it's the quadratic thing that generates rotations in the 1-2 plane in this kind of internal space which I've created of these, because my fields now live in this two-dimensional space. So I'm basically rotating in this two-dimensional internal space the fields live in, and it's this. Okay, so maybe better before let me not try and get started on that now. But okay, so the next and so the generalization is what you do is take is to any SOM for any SOM, and then you're going to have then remember Lie SOM is equal to the is equal to antisymmetric matrices. And so what you get so then for any pair of indices, you get, instead of just having one of these guys, you have one of these guys for any pair of indices. And let's see, so you get minus I Q hat JK, and it's going to be so for J less than K, for any pairs of two different indices, and you get minus I. Same kind of thing here, but it's just pi hat K of x vector I hat J of x vector minus J. And you can write the similar thing in terms of the p's. So, okay. So what this gives you is that these satisfy the commutation relations. Relations for the Lie algebra of SON. Okay. And so what we've created here is by taking, so if we had a single scalar field, what we created this quantum field theory with the state space that the Poincare group acted on. Now, by putting together m of them, m kind of non-interacting different scalar fields, we've put together a theory which has got not just the Poincare group acting on it, but also the this internal symmetry of the SOM group, and so this is kind of a standard example of the so-called internal symmetry, and we're going to be interested in these internal symmetries. What we're going to do next, because it turns out that the way you actually, the most interesting way of generating interactions in these theories is to use to look at theories with internal symmetries, and then to turn these into to do something which I'll start and explain next time, called gauging the symmetry. So you kind of think of these internal symmetries as being independent at every different x, and then you create a consistent theory which is invariant under these independent SOM transformations everywhere. It's called a gauge theory, and those kinds of theories will introduce interesting notions of how to get interactions between particles, which are kind of purely based upon this gauge symmetry. So we'll get to that. But the for next time, let me say, just we're going to go next time. So I'll get into the gauge symmetry next time. But next time, I'll start with the complex scalar field. And so what we'll do is instead of thinking of it as a pair of real, it's a pair of real scalar fields, but we're putting them together and thinking of them as a local complex variable at a point. And so we're thinking of something like phi1 plus I phi2 as this, and what we will find. We'll find again that you have to have two kinds. You have two kinds of annihilation and creation operators. Yeah. So instead of what I did here, I had annihilation creation operators A1 and A2, and then the SO2, the symmetry, kind of mixed them together. So what you do here when you try to introduce a complex variable here is you're taking this SO2, which is mixing these two real things, and you're creating, +1 plus I times the other and 1 minus I times the other, and you're then diagonalizing this SO2 action into something with charge 1 and something with charge -1. So this goes way back to something we did way at the beginning of the class, kind of asking, what is, how do SO2 representations act on R2 when you complexify it? It's that calculation. And then what you typically do is you give them different names, and so you have your original A of P vector and A dagger of P vector, but also B of P vector, B dagger of P vector. And these you think of as being particles. So these things, you create and annihilate particles. And by doing this and diagonalizing the action of Q, these are creating and annihilating something that has charge 1, that has that's an eigen things that are eigenvectors for that Q operator. And here these are also diagonalizing the operation of the Q operator, but now with a -1. So these are creating and annihilating something that are called antiparticle, that has charge -1. They're called antiparticles. And so what's going to happen? I'll say a bit more about it next time. But basically, the theory then becomes a theory of distinct. The real scalar field theory, you could think of it as, well, you've got particles and antiparticles, but they're the same thing. That these guys are actually the same operators as these guys. That phi1 is equal to phi2, if you like. But if you but this is separate. But you find some very confused. What I want to just, so I'll go through that next time, and then I just want to quickly point out that there are the fact that you've got kind of two different complex structures going on here. You've got this complex structure you're putting on this pair of variables on this R2, and then you've got this complex structure that you're putting on all the solutions in terms of positive and negative energy. And the fact that there's two different notions of complex structure makes the quantization of this thing a bit confusing. And so you find, anyway, so yeah, if you, anyway, it's a somewhat interesting story. I'll go over that at the beginning of next time, and then go on to use these internal symmetries to talk about how you so-called gauge them, and how you create these things called gauge fields that you couple these things to, and that you can get interactions. So that's where we are now. Okay, better stop now. So any questions about any of this, or about anything about the? So at this point we're pretty much done with the real scalar field, and the only thing we're going to be still doing some more with is these internal symmetries and complex scalar fields, and how they couple, and how to couple them, and their gauge symmetry a little bit later. But the real scalar field, that's kind of all I have to say about it. And any other questions? Okay, well, if not, so I'll stop. We'll stop now, and as usual, I'll be around. I should be around for a while later this evening. So please do come back and say hello, and if you have any questions, come back later. And also, we'll we should hope to start talking to you all next week about the whatever projects you'll be working on. Okay. Okay. So bye for today.
Thank you. Thank you.